Good friend of mine, and also one of the driving forces behind DDDPerth conference itself. And last year, Ashley gave us a wonderful, gentle introduction to functional programming, so he's back this year again, promising an equally gentle, be kind to us, introduction to quantum computing. Please welcome Ashley.
Okay, hello everyone. Thank you for coming along. Quantum computing is a very interesting topic and I think really significant. So I think you've chose the right talk to come along to. It's going to be a gentle introduction in the way a ride on the space shuttle is gentle, at least the takeoff. It's going to be a bit fast and furious. There's a lot to get through. But hopefully if you can keep up with me most of the way and follow most of what I say, I think you'll learn something and see how amazing this quantum computing is. So the first thing here to talk about is get some history. Way back in the days in computing, we started off with analog computing. Maybe some of you remember the old slide rule here. And the idea here is you use a property of classical world, like the length of a ruler, to calculate logarithms. And on the right-hand side here, we had an analog computer for calculating exponentials. You made up particular circuits, and the voltage in that circuit, due to the capacitors and resistors, would show an exponential sign, so you could use it, put in one voltage, and calculate an exponential. So we had these things called analog computers based upon classical physics. And these were great, but of course along came our digital computers, classical digital computers. And these were fantastic. These are based upon classical physics, although they use semiconductors to implement them. And in fact, a part of classical computers, they try to abstract away from the physics. Like a 1 and a 0 or a true and a false. It doesn't matter whether it's 0.9 volts or 1.1 volts, it's a 1. It doesn't matter whether it's 0.05 or 0.1 volts, it's a 0. So they're trying to abstract away from the physics to do classical digital computing. And we know about classical digital computing. It's all about ands and ors and nots and putting them all together to process the bits. Well, there's something new on the block. It's called quantum computing, and it's crazy. It's the next revolution in computing. And I don't say that lightly. It's going to be really big. And I want to try and explain it to you today. It's based on the quantum world, not on the classical physics, quantum physics. But I have to be careful here because the quantum world is quite bizarre. And so you may find your head exploding. So I can't guarantee anything or promise you, you may not explode. In fact, head exploding syndrome is a real thing. But hopefully we'll get through it without your head exploding. We'll see how we go. So a couple of things to talk about introduction here. This is what I want to talk about today. I want to give you an overview and I've done that. I want to give you quantum mechanics, some basics to help you understand things, because the quantum world is really different than the classical world. Talk about how we do computing in the quantum world. Talk about quantum computers. What do they look like? What they'll be made of? And see some applications where they become really useful. And we're starting to see something along those lines already. And we'll wind up and talk about the future. Some other points just about myself here. I have a background in academia, in physics, computer science, AI, and IT. But I also like to work in industry, consulting and professional training. I've done jobs around Australia, across Southeast Asia, and in the US and the UK for companies like Apple and IBM and the Commonwealth Bank. The last 10 or 15 years, I've been focusing on innovation, working a lot with startups myself. I've done some accelerators, and now I mentor and coach in accelerators. I focus on the lean startup approach with customer development, and I run the Lean Startup Perth meetup if you're interested in doing startups. My ventures myself, I've been involved with 3 major ones. My current one is Innovately, which basically provides consulting services around this lean startup with customer development innovation. Also, I had a software development company, and I focused on event-driven microservices and CQRS. I've spoken about that previously at this conference, and cloud. And I have a startup on my own, which is in higher education space, trying to change the way higher education works. It's called Acavista, but it's still very early stage. So enough about me. Let's thank our sponsors here, our amazing sponsors. Of course, we couldn't do this conference without sponsors. They're the ones who provide all the money to let you guys come along. And it's great to see so many local companies here supporting the conference. It's wonderful, a wide array of sponsors there. So thanks to them. All right, so whoops, we jump on there. So we're going to start now. We're going to go down the Alice in Wonderland wishing well sort of thing. And hopefully we'll be okay. But stick with me. We're going to talk now about quantum mechanics or quantum physics. Who did some quantum physics in their high school or university? A few people? That's good. For the others, it might seem quite strange, but just try and follow. The reason it does seem a bit strange is that we all live in the classical world. We live in a world of, meters and kilometers and normal gravity and so forth, and big, massive objects like ourselves. You throw a ball and it goes straight and it drops to the earth under gravity and so forth. This is the world we live in, the classical world. This is the way we understand things. But quantum mechanics is very different. It's about the microscopic or the atomic size world. And there's no reason that has to behave the same as our world, and we'll see, in fact, it does behave very differently. So this is quantum physics, the first experiment which demonstrated quantum physics. Basically, there was an electron gun, and it would fire electron guns at a little wall there which had 2 slits in it. And then we have a sensor on the side of the wall. And of course, when you fired some of the electrons, some went through the holes and made a mark on the sensor, and some of them bounced off the wall and didn't go through the holes. So what people expected was, if you did this experiment with single electrons, after a while you'd get a pattern like this. 2 areas where the electrons were all going through. But they were surprised when they did this experiment that what they actually saw was something very different. It was like this. And this is basically a classic thing we see a lot of times. It's an interference pattern made by waves. The troughs and the peaks of the waves, where you get cancellation and superposition of the values. So this was a strong thing to indicate that these electrons weren't behaving like particles and just going through the slits, but in fact they were behaving like waves. So the electron wave came here, 2 separate parts went through the actual slits, and then those 2 separate waves were interfering and causing the pattern. But remember, the pattern over there isn't like some painting on the wall. It's statistically where the particles will go. It's a probability distribution. So these waves aren't like water waves or air waves. They're waves describing the distribution of probabilities associated with this electron. Now, this is quite amazing to think that an electron is behaving like a wave. And this was the start of quantum physics. The things we learned from this was the electron goes through both slits at the same time. That's pretty freakish. We don't see that in the real world. And the electrons are both particles and waves. Again, that's a bit strange. We see waves and we see particles, we don't see both things. And a lot of people said, oh, that can't be true. Something's wrong. Maybe there's 2 electrons are doing things. But remember, we're sending 1 electron through at a time. It's not going through, interfering with other electrons. It's 1 at a time. So people said, oh, yeah, what happens if we get a detector there and we try and detect the electron, which one it's really going through? But luckily, or strangely, they found that when they did that, they put a detector there, they actually detected the electron. Suddenly, that pattern changed back to this one. And why does that happen? Well, you have these waves, this probability wave, but when the electron interacts with the detector, or a macroscopic system, a big system, it actually collapses into one of the classical things. It becomes more like a classical electron, like a particle. So when you put the detector there, it behaves like a particle. When you take the detector away, it behaves like a wave. Strange things. This is quantum physics. So the point here is, in quantum physics, we have a concept of coherence and decoherence. Coherence happens when the electron's on its own and not interacting with the environment. So it's doing all the wavy type stuff. Decoherence is when it interacts with the environment and the wave function collapses and it now works like a particle. That's wave function collapse. So when it's fully isolated, the electron behaves like a wave. It's said to be in a coherent quantum wave state. When it actually interacts with the macro environment, then it collapses and becomes a classical state. So this is the details of quantum mechanics. You don't need to worry about these equations. This is Schrodinger's equation. These are the guys who invented quantum mechanics nearly 100 years ago now. And the solution of this equation is that wave, that probability wave I was talking about, which describes where the electrons will go with what probabilities. That's very important. Quantum physics isn't deterministic like classical physics. It's probabilistic, and that's very different. So let's explain this. Look at 2 or 3 of these concepts. The first one is quantum superposition. So here we have an electron, and this electron has a charge and has a spin, and it causes a magnetic field. And that magnetic field can be up or down. So we can say the electron can be in two states, the up state or the down state. It can't be halfway, it's either up or down. And we can actually see this is not two different electrons, this is one electron in both the up and the down state at the same time. That's what superposition means. You're in both states at the same time. Like the electron was going through both slits at the same time. So don't think it's separate. The way we describe this wave function here is we say it's combined of some of the upness and some of the downness, and this weight here is used to calculate the probabilities that when you measure this electron, would you find it in the up state or would you find it in the down state? And this one here is balanced, so it's half-half. If you measured it, you'd see half the time it's up and half the time it's down. But of course, again, it's just one electron in both those states at the same time. Now, they don't have to be equal. These electrons have this electron has different weightings. So it's more likely to be in the up state than in the down state. So when you measure it, you're more likely to get up than you would get down. So there's a famous experiment you may have heard of, Schrodinger's cat, where Schrodinger said, this is absurd, you can't be in both states at once. If we put a cat inside a box and we had a radioactive particle here, if that radioactive particle decayed, it would cause the hammer to crash the bottle of cyanide here and kill the cat. If it didn't decay, then it wouldn't kill the cat. And Schrodinger said, well, that's absurd. So you're saying to me, when I can't see inside this box, the cat is both dead and alive? Can't be. That's ridiculous. And in fact, it is pretty ridiculous. If you learned high school quantum physics or university, they probably told you that until you observe that cat, it is either in one or the other states. But our current understanding of quantum physics is that when that radioactive particle interacts with the macroscopic system, the hammer or the device here, then actually it will collapse into one of the states. So the cat will actually be dead or alive in this circumstance. Macro systems don't operate like quantum systems. Only the particle inside here operates like a quantum system. And that's important too. Okay. Separate thing to look at here is called quantum entanglement, and we'll talk about this later on too. It's important for quantum computing. Think now we have two electrons here. Both of them can be in the up or the down state. If we made them in a way that they had a wave function which only contains two possible states, both down and both up, and we can construct these electrons into this particular wave function. All right, so it's this much both down and this much both up, or the other way around. Now, what would happen if we separate these and we do a measurement, we interact with this one to find out whether it's up or down? If we found out this one was down, what do you think this one has to be? Any ideas? No, because the state here is down, down, or up, up. If this one is down, it has to be in the down state. If we measure this one and it's up, because the wave function says it's only split between these two things, the other one has to be up. So there's a correlation between the states because these two electrons are quantum entangled. Their wave functions are dependent upon each other. This is pretty strange. They're joined together some way. And people didn't believe this for a long time until they did experiments inside the laboratory and proved this actually happens. And it's even quite freakier because you can take an electron on Earth, and the Chinese have done this, and take that electron, entangle with one down here, and put one on a satellite. When you measure the electron down here to find out is it up or down, suddenly the one up here is up or down too. They're correlated. And in fact, this is actually instantaneous. There's no information taking time to travel between these two. They're connected, no matter how far away they are. Now, for us who live on the world on the ground here, that seems pretty stupid because we're used to things that interact with each other, affecting each other, you know, influence, cause and effect. But here, something way away is getting affected by something way down here, quantum entanglement. And this is proven. They've done it on the satellites, and it basically showed that they were entangled. So two things there we've seen. Einstein called this the spooky action at a distance. And it is pretty spooky, but it actually happens. It's real. It's the quantum world. A famous physicist here, Roger Penrose, he said, quantum mechanics makes absolutely no sense. So if you don't understand this stuff, you're in good hands. This guy, quantum physicist, he says it doesn't make sense either. And the reason it doesn't make sense is you can't think of it and understand it in terms of our everyday physics, our classical physics. It's what happens in the quantum world. Famous physicist Richard Feynman, he said, if you think you understand quantum mechanics, you don't understand quantum mechanics. It's that complex and strange, right? And he actually, when he said this, a year later, he went on to win the Nobel Prize for his research in quantum physics. So he knows what he's talking about, right? So it's hard to understand. Don't be worried. And you may think, well, maybe it works like that, but maybe we just examine a bit more. It'll work more like the classical world. But no, this is how the world works at the quantum scale. Quantum physics is the most accurate and the most tested theory in the history of science. It's amazing. Quantum physics predicts certain values of physical constants. And when you go and measure them in the real world, they're precise to 11 to 12 to 13 decimal places precision, plus or minus 28 at the end. We don't have any other theories that are that accurate. So a lot of the quantum physicists, when people start philosophizing about is the world really like this, they just say, shut up and calculate, because it gives you the right answers, right? This is what our classical computers are based on. This is what most of modern technology is based on. It just works. Quantum mechanics is the reality at the quantum level. So that's pretty strange stuff. And you may be having an exploding head at the moment. A bit hard to understand that. But just think about it. We have superposition of states and we have entanglement. And we're going to try and build some computers based upon these two physical properties. So quantum computing. What's that about? Well, as I mentioned, classical computers focus on building systems based upon classical physics, or abstracting away from the quantum physics, getting rid of the noise and hiding that stuff. Now we have a lot of problems with classical computers because we're getting down to the level where these quantum effects start to happen. We don't want that to happen, so we're limited. We try and stay classical. But we want to try and build computers which benefit from these quantum physics. And when we're talking about quantum computers, we don't talk about normal bits, we talk about quantum bits, or they're often called qubits for short. And these are a core part of the quantum computing approach. So let's try and compare classical bits with quantum bits. So here we have one classical bit. And as you know, it can be a 0 or a 1. There are two states, and it can be in one of those states at a time. It's either 0 or it's 1. Quantum bits, as we know, are different. This is that quantum superposition. A quantum bit can be in both the states 0 and 1 at the same time. Now, it's not 0.5 or 0.6. It's the two states, but it's a mixture of those states at the same time. Quite radical. If we keep on doing this, of course, in classical computers, we have 2 bits. We have 4 states, but we're still in one of those 4 states. Quantum computers, if we have 2 qubits, we have 4 states, but we're in all of those 4 states at once, if we decide to be in all of those 4 states. And we can keep on going. 3 bits, 8 states in one of those states. The quantum one, 3 bits in 8 states at the same time. Now it gets interesting. Think about n bits. N classical bits, 16, 32, 100. You can have lots of possible states, but you're still only in one of those states at a particular time. This is where it gets interesting. For a quantum system, if you have n bits, you're in 2 to the n states at the same time. And there's a distribution about how much of each state you're in. Maybe this state you're in some more, and this state you're in less, and this state you're in more. Quantum states, quantum bits are very different. To show you how this is important, think about 300 quantum bits. Not too big a number, 300. If you had 300 quantum bits, then you have 2 to the 300 states that you're in, and that's more states than there are atoms in the universe. It's a lot of states in 300 quantum bits. And if we can use that for doing some sort of processing, we can do amazing stuff. So the approaches to quantum computing, there's 2 approaches. We're pretty early stage still. One I call digital quantum computing. It's analogous to the digital classical computing, and one I called analog quantum computing. It's an analogous to the analog classical computing. And this approach, the first one we'll focus on mostly, and it's similar to the traditional approach. We process these bits, but in different ways. The second approach, we use the analog computer to simulate quantum systems, because it turns out simulating quantum systems is actually quite hard to do on a classical computer. We want to do that to understand quantum world. So let's have a look at the gates, or the processes, or the operations we have in a quantum system. These gates, like we have logic gates in a classical system, these apply to the qubits. So we apply an operation to the qubit. So we have gates like the X gate, which is similar to a NOT. We have a Toffoli gate, like an AND. We have a number of different operations here that can apply to one or more of these quantum bits. It actually turns out that these three operations here are equivalent to classical computing. They make the quantum computing a universal computer, just like a classical computer. So anything we can do in a classical computer, we can do in a quantum computer, but we probably won't want to. We'll probably focus on the things that it does differently. We won't go into the details of these, but they're just different operations applied to these quantum bits, which are in many states. So what about the processing in a quantum computer? What does it progress like? Well, we have this diagram here which explains things. These are our quantum bits down here. And across here we can see we're applying different operations. We apply the H or Hadamard operation here. Then we apply this operation here between these two bits, another operation here, and then this one. And this one shows here we're measuring the quantum bits. We're interacting with them to find out what their state is. That causes some quantum wave function collapse, but we can keep on going because not all of the system is collapsed. So this is how we describe processing in a quantum computer. But be careful here. Don't think this is like the electrons are flowing through here and these are gates. The quantum bits actually stay where they are, and we just apply these operations to them. So this diagram is really showing you what happens over time to these quantum bits. We do these first, we do these, and we do these, and so on. So this is the processing we do to quantum bits. There's some problems with quantum computers. These quantum bits tend to decohere over time. They lose their coherence, their quantumness, and they become more classical. And this introduces errors, high error rates. As they interact with the environment, any interactions, noise, sound, thermal interactions. So to make reliable quantum computing, we have to get some sort of quantum error correction. Just like we error correct some of our RAM now, we're going to do the same thing for quantum memory. And in fact, this has already been done. A guy has already written the algorithm. The good news is the algorithm to do quantum error correction to make sure our quantum bits are reliable. We need them to be reliable. That's the good news. The bad news is that to make one quantum bit reliable, you need about 1,000 extra quantum bits to provide redundancy and make sure it's reliable. That's quite large. What can these quantum computers compute? If you know about the PNP problem, the polynomial time problems and the non-polynomial time problems, in quantum computing we introduce a new thing called the bounded error quantum polynomial time calculations. These are the things you can calculate with a quantum computer. We don't know for sure, but we know at least that quantum computer can do everything that a classical computer can do in polynomial time. We think possibly that BQP is greater than P. We can do things more practically, more efficiently in quantum computers. But that may just be because we haven't found the right algorithm for our classical computers. But I tend to think there's extra there in the quantum computer, so maybe we are greater than P. But don't think that quantum computers are going to solve all our MP problems. There's no silver bullet for that. It doesn't give us a magic solution to solve exponential problems immediately, but it will help us solve some problems faster. So that's pretty good news. Maybe your head's still exploding, but hopefully you're following here the idea of a quantum computer, the quantum mechanics, and using those with quantum bits and doing processing. Are you following me? Okay. Hope so. Let's have a look. What's the next thing? So let's look at the physical parts now, the quantum computer itself. What does it look like and how does it work? As I mentioned, there were two types of quantum computers, the digital ones and the analog ones. We'll focus on the digital ones. And the way they currently work is there's two approaches. One is called ion traps. They take an atom, they get rid of some electrons, so now it's positively charged, and they use that positive charge to trap it in an electric field. So they can isolate it from everything else, they can cool it down, and now they can use its quantum states to build qubits. The other approach, which is very common, is supercomputing circuits. They have a little silicon circuit, but they cool it down to nearly absolute zero. And now it becomes a superconducting circuit. So now it actually shows some quantum properties, and you can use those quantum properties to build your quantum bits. The other one uses supercomputing circuits as well. This is an example of a quantum computer chip. As you can see here, it's pretty clear. These are the actual qubits. You see the little bits there? So basically, I think it's 16 qubits on this one. They're little loops where you can get superconducting things happening when it's cooled down to really close to absolute zero. In fact, it's a couple of order of magnitudes colder than outer space. Millikelvins. Very, very cold. But you can also see here some circuitry which actually produces electric fields to allow us to interact with those quantum bits, to perform the operations on them, to change their quantum wave function. So this is how a new quantum computer chip looks currently. But of course, that's just the chip. We have to put it inside some infrastructure. As I mentioned, you need to keep this near absolute zero. So we need to have a cryostat with many layers so you can cool it down to get down to this absolute zero temperature, or close to it. We need to also isolate it from any vibrations. We need to also isolate it from any electromagnetic fields. Because if that quantum bit interacts with the outside world, radiation or vibrations, it'll become a classical thing again, and it will lose its quantum state. So we have to isolate it to keep it quantum. So we cover this up in a cylinder, and we make it into a cryostat here. It can be cooled down. And now we have a whole lot of electronics to actually control that chip, to affect the chip, to make measurements, to do transformations. We have a whole lot of electronics, a control processor layer to control this stuff. And then we have traditional computers, which actually program these control systems. So I think that's how you'll see quantum computers for a number of years going forth. Basically a classical computer controlling electronics which affect the quantum chip. So we're still using classical computers to control this stuff. Now this looks pretty old, this looks pretty bulky and out of, not very state-of-the-art sort of thing. But this is our first attempt at quantum computers. Remember what our first attempt at classical computers looked like. This is Australia's first digital computer, the CSIRO built. So we're at this stage currently with quantum computers, and we've got a long way to go. But even though we're at that stage, some people these days, some companies, put a shiny box around their quantum computers, and they sell them. This company, D-Wave, sells quantum computers which have 5,000 qubits, which sounds like a lot, and it is. But the problem is these qubits aren't very high quality. They decohere very quickly, and people don't believe much quantum stuff happens there. Still, they can use them for certain calculations and for simulating quantum systems, so you can buy one for $10 to $15 million, I believe. IBM also build a quantum computer that you can actually buy. How do we program these things? Remember, we program on a classical computer to control the electronics which control the chip and make it do things. And a number of companies have libraries to help you control or process this quantum stuff. Microsoft have a language called Q#. Basically, it's a DSL to help you do quantum operations on qubits. So if you have a look through this code, it's not hard to understand. Here we're applying a C0 operation. One of those transformations, we're applying it to a particular qubit to get from here to there. Then we provide a H operation on this one. And down here, we're doing a measurement of certain bits. So a DSL to control the electronics to transform the qubits inside the quantum computer. And that's how you program a quantum computer currently. It's sort of like the machine level programming of our old computers. So there are issues, as I mentioned, with quantum computing and quantum computers. There's a decoherence problem, that we lose coherence, we come out of the quantum state. There's a difficulty with input and output. Who would have thought input and output would be difficult? Because it's hard to get input into all these states, to put the quantum electrons into certain wave states, and it's hard to get the information out. Because if you try and measure the state of the quantum bits, you make them classical again. so you lose all your quantumness. So you have to do some tricky things to measure a little bit, but leave the system still useful. Also, I mentioned we have a short time of decoherence, so they only last in their quantum state for a short time. And how would you debug one of these systems when you can't interact with it? You can't do printfs or save to a log file. How do you debug this sort of stuff? But the truth is here that all of this is improving. We get better at doing this. We're finding out ways how to do this to program quantum programs. In fact, there are some current records in quantum computing. The record for coherence time, keeping in that quantum state, is 90 microseconds. It's not very long. Other systems get longer times, but they're not really quantum systems, like the D-wave ones. 90 microseconds isn't very long, but now we can show that we can actually perform the operations on these qubits very fast. A team of researchers at USW have shown they can do a qubit operation in 0.8 nanoseconds. So that gives us quite a bit of chance to do operations before we decohere and lose the quantum state. And the largest digital computer currently that I know of is 72 qubits, built by IBM, the bristlecone processor. And every year we get more and more. So it's basically growing every year. That's quantum records. There's a huge investment in quantum computing. I'll explain a bit why a bit later on, but companies like IBM, Microsoft, and Google have large research labs investing millions and millions of dollars to build quantum computers and to understand quantum computing. Similarly, there are a number of startups like D-Wave and another one called Rigetti. And in fact, the story is if you go into any cafe in Silicon Valley and start talking about quantum computing, someone will write you a check for $1 million straight away. Everyone's investing in quantum computing. And even the governments, the EU is one of the largest investors in quantum computing research. Similarly for the US and China, because they see it as the next revolution in computing. It's very significant. So, you maybe still have exploding heads, but now you're enjoying it with your friends as your head explodes. It's pretty radical stuff. It's not what you'd normally think about as computing or the way we do computing. But I want to show you in the last section here some applications of quantum computing. You'll see why it's really important and how it's really important. Because we're at an early stage in quantum computing, and we don't just want to copy all the things that classical digital computers do, we tend to find that quantum computers are problem-focused, not automation-focused. You don't build an ERP system or a CRM system or a banking system using quantum computers, because we can do that really well on classical computers. But there are certain problems in classical computing, in normal computing, which we have trouble solving, and quantum computers can help us solve those. Let's look at those. So there are 4 different types of problems that we can solve: simulation of quantum systems, search, factorization, and optimization. And I'd like to look at 2 or 3 of these and explain them to you, give you an idea of how it solves these problems. Before we do that, we talk about the first one, simulation. Here's another quote from Mr. Feynman. He said that nature isn't classical, damn it. That's how he spoke. And if you want to make a simulation of nature, you'd better make it quantum mechanical. And he was intrigued by the fact that this is a jolly good problem to try and solve. It's really hard. And in the past, it has been very difficult. If we wanted to simulate electrons in a molecule for chemistry, to see how these electrons interact, if we try and do that with a classical system, it's very, very difficult. Think if we had 40 electrons in our molecule, and they could be in 2 quantum states. But remember, they're in a superposition of all those quantum states. So you actually have 2 to the 40 states you have to try and store in memory. Actually, it comes down to about 130 gigabytes of memory you'd need to store 40 electron states in a quantum wave. That would be really tough, but if you could imagine you could get 130 gigabytes of memory, maybe we can these days. If you wanted to add 1 extra electron, 41, it's not just a little bit more, it's 2 times more. So now you need 260 gigabytes of memory. So the classical resources you need to solve quantum simulations go up exponentially because the number of states goes up exponentially. So this is why quantum computers are really good for simulating quantum systems. If we have 40 bits, we could simulate our 40 electrons. If you want to add in 1 more electron, we just add in 1 more bit. And in fact, quantum simulation using quantum computers to model the behavior of chemicals and so forth is basically making the chemists really happy. They now think they've solved the problem of simulating and understanding matter. No longer is it difficult to simulate. We can do it and understand it. We can build whatever matter we like because we understand the chemistry and how these applications, how these molecules and atoms interact. They think it will have huge implications for the pharmaceutical industry. $1 trillion industry, they're saying, in using quantum computers to simulate atoms, to build the materials and the chemicals we need for our pharmaceuticals. Quantum simulation is not just a little bit faster, it's thousands of times faster than classical computers trying to simulate a quantum system. It's exponentially better. That's huge, exponentially better. So the first thing that quantum computers can do is they can simulate quantum systems in the real world, which is great. The second thing to do, which we can do with quantum computers, is we can search. Now think about classical search. If you had a file with n numbers in it and you wanted to search through and find one of those numbers, it's an order of n problem, classical search. On average, you have to go through about n divided by 2 before you find the one you want. With a quantum computer, we can prove, there's an algorithm which is proved, we can do it in the order of square root of n. And this is quite amazing. It's quadratically better. If you think about it, if we were trying to search 10 billion things to find a needle in a haystack, in the classical computer, that would require on the order of 10 billion operations, quite a few. With a quantum computer, it's a square root of that, just 100,000. So a lot faster to do search. One problem area that quantum computers can help in. An example of this is the traveling salesperson problem. You may have heard of this. This is a problem where you have a salesperson, or a tourist in this case, who wants to visit a number of different sites. And he knows the distance between all of these sites. Which ones should they go to in which order to see the most and travel the least distance? It's a minimization type problem. But really it's a search problem too, because you could search through all the different possible routes and find the one which is the lowest. And in fact, this is an n factorial problem, because your first choice is n, your second choice is which one I go to, n minus 1, and you keep on going, n factorial. You ever tried factorials on your calculator? By the time you get to 110, you blow up your calculator, because factorials get very large very quickly. But the nice thing is, quantum can do this search in the order of square root of n. So even though it's huge, it can do it quite quickly. It can solve this problem. And the way we do this is, some guy named Grover suggested a Grover's algorithm, how to do this. And basically here is that diagram again, showing you our quantum states, and we're applying operations, but these are like modules or functions with a whole lot of operations inside. So we do this particular step, then we find a short route, yes or no. We do this step and check for the short route. And he described these operations and these things you do in detail. Some of them are quite complex, some of them are quite classical. To calculate the square root, the shortest route, or the length of the route, you have to do some classical operations. But remember, quantum computers can do classical operations. So we have a whole lot of them there. And the thing is, once you follow this algorithm, it can actually solve this problem in order of square root n time. So in the past, traveling salesperson, when it got large, was too hard. Now we can do a lot more calculations and using the quantum system. So how does this actually work, this quantum approach? It's hard to explain. Remember, these operations are operating on the qubits and changing their state in the quantum space. That's what they're doing. But it's hard to give an analogy to this, so the best thing I saw was this one. If we lived in northern Africa and wanted to get to the Iberian Peninsula, just across the water here, if we didn't have a boat and we had to do classical search, we'd go all the way around through Europe, take a long time to get there. But quantum computing gives us a new way to travel. It's like the boat. We can just go quickly across this distance and be there in a short amount of time. It doesn't solve the problem completely. If this long distance is still huge, we're in trouble, but it's a lot better than taking the land approach. The boat solution, the quantum solution, is much better. Quantum TSP, okay. So we saw that one, yeah. Okay, so the second example, sorry, it's number 3 there, is quantum cryptography. The idea here is, can we use quantum systems to build cryptographic systems or to crack our current cryptographic systems? And we have some bad news and some good news. The bad news is in 1994, Peter Shor wrote an algorithm for factoring integers, large integers. And it used something called a quantum fast Fourier transform. It basically looks for periods of repetition in numbers. And he said that you could use this algorithm to factor a large integer. And you could do it in polynomial log of n time, which is a lot less than we currently can do it. So it's basically almost exponentially faster than the most efficiently known classical algorithms. So the bad news here is, if we have a quantum computer that can do this, it can break all our current encryptions, which use large prime factors of integers. That's the bad news. The good news is this was developed in 1994, and we haven't really developed a quantum computer that can do it at the moment, and probably not in the next 10 years we'll be able to do it. But in 10 years' time, probably we'll be able to break our current encryption. This is a diagram showing you how Shor's algorithm would work. Some of the classical operations, some of the quantum operations you'd do. It's a prescribed set of operations on these bits, and it gives you out the period or the repetition or the integers, factors of this large integer. No one's implemented it yet, but it's potential there once we get a computer to actually do this stuff. So there's a warning here. Quantum factorization is coming. It breaks public key cryptography. Now, as I mentioned, it may not happen next year, it may take 10 years, but imagine if we had to change all of our cryptography. Because when this stuff happens, people who get these sort of computers will be able to break into all information that's currently stored in asymmetric key encryption, anything that's encrypted. It'll also be able to break into all communication that is currently encrypted. HTTP communication, SSL stuff, all now break into it. So some Russians or Chinese break this stuff, will actually be open to them eavesdropping. So this is why the big governments and the military in the US are putting a lot of effort into finding the next cryptography to replace our current approach, something like quantum cryptography perhaps. So that if they can find a solution, it'll take 7 years or so to roll it out exclusively and change all our encryption. We'll be ready when the quantum computers come along and actually break our encryption. So something to worry about, something to think about there. The quantum solution for encryption uses that idea of entanglement. If we can take an electron here, or a number of electrons, and split it apart and give it to somebody else, then they can look at the electrons and see what our electron's like, and that's like sharing a public key. And we can do that privately and instantaneously. So we can use the entanglement approach of quantum systems to make quantum cryptography. But there's no time to go in there. So the last thing I want to talk about just quickly is machine learning and AI. The machine learning and AI involves a lot of systems of linear equations, multiplying matrices and multiplying matrices. And quantum computers are actually quite good at doing this, very good at doing this. You make up a whole lot of quantum states and you can process them like you would matrices. But the problem with quantum computers is you can't really get the information out easily. You can't find what is the solution to this quantum matrix multiplication. But what you can find is properties of the solution. Is it this or is it that type of solution? General properties, holistic properties. And people have actually written recommendation engines, algorithms using quantum operations that can perform recommendations like Netflix does. And the way the traditional systems do it is they look at all the movies you've watched and try to recommend one based on those. They're found with a quantum system, just by looking at a log number of queries, a log number of your movies, so a much smaller number, you can make a good recommendation. So in the future, we may use quantum systems to do recommendation engines, but also help with general AI algorithms to speed them up, to make them a lot faster. So there you go. That's what I'm talking about for quantum computers today. I hope that hasn't really blown your mind. Maybe it's expanded your mind. Maybe you've learnt something or got a glimpse of what quantum computing's like. As I said, it's quite significant. To wind up here, I shall make a summary. The first thing is, hopefully you've seen that quantum computing is a really new type of computing based on quantum physics, not classical physics. Hopefully you've seen that quantum computers are built around operations on a number of quantum bits, Smallish number. We probably need to get to thousands before we can do things really well, but not necessarily millions. And quantum computers seem to be able to solve some problems much faster than classical computers did. But they don't solve all problems. They're not the magical solution to everything. There are a number of resources you might want to have a look to if you want to learn more about quantum computing. If you want to learn more about the theory, there's a great paper or article or book written by the National Academy of Science in the US, all about quantum computing, the process, the progress, and the prospects for the future. And also major computer companies like Microsoft, IBM, and Google have libraries where you can actually go and start to play around and code. And that code may actually interact with a system which is a simulation of a quantum computer. So you're ready when quantum computers come on. But some of them actually have small-scale quantum computers, say 5 qubits, where you can actually run your program on a real quantum computer for free and try things out. But there's no large-scale quantum computers available at this time. So, what are our milestones and where are we at with quantum computing? We're nearly finished. This shows you a number of different milestones we can go through with quantum computers to get to the final end game. This side here is the analog computers, simulating systems. There's not too far to go. With this one here, a long way to go. The first stage is probably where we're at. We've got small systems of tens of qubits. We haven't gone that far. The first real major milestone with quantum computing is when we make some digital quantum computer that does something that's not really practical ever in a classical computer. And that's what we call quantum supremacy. Quantum computers can do something that a classical computer can't do, or at least the algorithms we know currently. That's the next step. But there are a lot of steps to go through there. So if I had to think about the future, I haven't got a crystal ball, so I can't see the future. But if I had to think about it, what would I say? Well, I'd say that quantum supremacy, that's when quantum computers are better, is coming. Probably in the next few years. So look out in the press, in the technology press. If you hear talk of quantum supremacy is achieved, you know things are really heating up fast, getting important. But what about the future, the distance? Well, there's one thing about humans here and technology that I know is true, and we'll explain this, what the future is going to be like. If you think about the future, humans tend to predict the future linearly. We see the past and put a nice linear line to the future. And so things don't change very much when you look linearly. Humans predict linearly, but technology, it improves exponentially. So we're thinking that the computers are going to just be like this. It'll take 20 or 30 years, but it does this. So one thing I can say for sure is quantum computers are going to happen sooner than you expect them to, because you're predicting linearly. They're going to happen a lot faster. Just like the internet did and voice recognition did and all this stuff. It came, one minute we haven't got it, next minute we've all got it. And it's just natural stuff. Quantum computing will be here soon. So whether you'll get a iPhone QC or not, I'm not sure. There's no reason why we can't have room temperature superconducting stuff and we can fit it inside a device like this. So I'm not going to say never. People who say never always prove wrong, but possibly. So that's the end of my talk, and we've talked about exploding heads. And here's one head I would like to explode, but maybe not. But even if your head did explode today, hopefully you saw some beauty along the way, and it was interesting, and you saw an elegant glimpse into what quantum computing and quantum computers and programming of quantum systems and the solutions that they can solve will be like. Thank you very much. I don't think we have time for questions, but that's all. Thank you.